Hello, welcome to the research presentation of the title, Assessment of Wave and Tidal Energy Potential in Coastal East Malaysia. So this is the outline of the presentation. I'll be the first presenter talking about the introduction of the research and explain about the technical and economic evaluation. Then Desmond will explain about the wave and tidal harvesting technology and devices and the site selection criteria. Then Govin will justify about the site selection, explain about the data collected in this research and the power generation from each site and the LCOE. And finally, Chiang will end the presentation with the environment analysis, comparative analysis, and the geographical sustainability, and concludes the presentation. The current state of Malaysia is pushing the transition towards the green and sustainable energy resources. And East Malaysia, which is Sabah and Sarawak, has long coastline, about 2,600 kilometers, are strongly exposed to the ocean dynamics, typically the waves and tides. Hence, we can look at the ocean as a high potential renewable energy alternatives. There are few literatures discussed about Sabah and Sarawak have many unelectrified villages and households. This is due to the difficult terrains and poor infrastructures and poor access to grid lines. Because of that, the limited electricity affects the education, healthcare, and some economic development. So the aim of this research is to evaluate the geographical, technical, and economic feasibility of wave and tidal harvesting system in Sabah and Sarawak. And by the end of the research, we expect to identify the feasible location and recommend the appropriate technologies to support this rural area for electrification. So why tidal and wave, you might say? It is because wave have high energy density. Some literature claims that it is more reliable than solar or wind in terms of generation, and it is strongly influenced by the monsoon season. While tidals provides more predictable and consistent generation, and it has very low environmental impact. This table provides some of the wave and energy harvesting technologies, and our focus location in this study is Sabah, around Tawau and Sanakan, and Sarawak, around Miri and Bintulu. So these slides provides a literature explanation about technical evaluation of wave and tidal conversion systems around East Asia with a focus around East Malaysia. Starting with the regional potential, Sarawak and Sabah hold promising coastlines along the South China Sea and the Sulu Sea. Though local marine renewable energy research remains significantly underdeveloped here compared to more mature maritime nations. A key challenge here is the critical data gap. Most existing studies relies on satellite data and numerical model rather than a direct site-specific coastal measurement, which limits the accuracy of the findings. In terms of wave dynamic, East Malaysian water shows moderate potential with energy density ranging from 1.41 to 7.92 kilowatts per meter. Open seas like Bintulu and Miri outperform sheltered zones such as Sandakan and Tawau. For tidal resources, some literature claims that Sarawak holds stronger baseline than Sabah, thanks to greater tidal fluctuations and more favorable coastal geometry, though comprehensive assessments still remain sparse here. Despite lower wave heights and tidal velocities compared to global benchmarks like the UK or Portugal, marine energy systems are still highly viable here, particularly for small-scale remote islands and coastal electrification projects. Next is about the economic evaluation of ocean energy system. The first major challenge here is the deployment barriers. Ocean energy requires significant higher upfront investment than mature alternatives like solar PV or wind. This is driven by the specialized subsea equipment, complex offshore installation, and unpredictable operating environments. Compounding this are the elevated operational and maintenance costs. Restricted site accessibility makes OPEX particularly expensive, and offshore devices need continuous financial reserves to withstand marine corrosion, biofouling, and extreme weather conditions. In terms of cost structure, the total project expenditure is divided into 4 phases: pre-installation, CAPEX, OPEX, and decommissioning. CAPEX dominates, covering manufacturing, transports, and installation, while OPEX handles routine inspections and component replacement. And finally, the LCOE, or the levelized cost of energy, is the standard benchmark for comparing the competitiveness costs across the technologies. However, calculating a reliable LCOE for wave and tidal system remains highly uncertain, largely due to the lack of global commercial scale deployment and long-term operational data.
Thank you, Brian. So this project focus on two types of ocean renewable energy technologies. So there are wave energy and tidal energy. In this study, wave energy is considered suitable for offshore regions with moderate wave conditions, especially along the coastal area of East Malaysia. On the other hand, tidal energy utilizes the rise and fall of the sea level caused by the tidal movement. Compared to wave energy, tidal energy offers more stable and predictable electricity generations because tide flow regular natural cycle. Therefore, this project aims to assess the potential of both wave and tidal energy at selected coastal locations in East Malaysia. For wave energy harvesting, the selected device is the point absorber. This device converts the vertical motion of the ocean wave into the electricity through the movement of the buoy system connected to a generator. Point absorber was selected because they are suitable for moderate offshore wave conditions and require relatively simpler installation compared to larger wave energy system. For tidal energy harvesting, the selected system is the tidal barrage. So this system uses the height difference between the high tide and low tide to generate electricity. Seawater is stored within a tidal basin and released through a turbine during the tidal flow. The tidal barrage systems were selected because they provide stable and predictable power generations, especially in areas with suitable tidal range conditions. Therefore, these two devices were selected based on their suitability for the coastal condition in East Malaysia. Next, this slide presents the main formulas used to estimate wave and tidal energy potential. For wave energy, the first equation calculates the available wave power based on wave height and wave period. Since wave height is square, a higher wave can significantly increase the generated power. The second equation estimates the actual electrical output from the point absorber by considering the device efficiency and capture wave. For tidal energy, the first equation calculates the potential energy stored in the tidal basin, which depends on the basin area and tidal range. Finally, the tidal power output is determined by dividing the stored tidal energy by tidal period. These formulas are then used to evaluate the renewable energy potential at the selected coastal location in East Malaysia. For the site selection criteria, five main factors were considered. First is the distance from the coastline, because it affects the installation cost, cable length, transportation, and maintenance access. Second is the wave characteristic and water depth. Wave height and wave period influence energy output, while the water depth affect the suitability and efficiency of the device. Third is the seasonal variations, especially monsoon and dry seasons, because this can change the wave intensity and tidal pattern throughout the year. Fourth is the energy output, which is used to compare the power generation potential of each locations. Lastly, time dependency is considered because tidal level and environmental conditions change throughout the day, affecting the final power output. Thank you, and I will pass it to Govin.
Hello, I am Govindip, and now I'm going to talk about site selection and justification. So, for our assessment on the tidal and wave energy potential in coastal East Malaysia, we have chosen four different site locations, which is Miri, Bintulu, Tawau, and Sandakan. And the exact coordinates to implement these wave and tidal energy systems are shown in the site selection table here. The reason for choosing these four locations is because they are located along the South China Sea and Sulu Sea. They are also exposed to open sea conditions with consistent wave propagation, and there is presence of tidal currents which is suitable for tidal energy generation. And the high marine renewable energy potential is there in these four locations with minimal coastal interference. Now, Let's take a look at our wave and tidal data collection. So for wave data, we have collected the average wave height and average wave period across both the monsoon and non-monsoon seasons for all four locations. As you can see from this table, Bintulu was recorded to have the highest average wave height across both the monsoon and non-monsoon seasons. For tidal data, we collected the average tidal range and average period for spring tide and also neap tide. And as we can see here, Tawau was recorded to have the highest tidal range for both spring tide and neap tide. Now, let's look at the wave and tidal power generation graphs. So for wave power generation, Bintulu was recorded to have the highest power generation recorded in a day for both the monsoon and non-monsoon seasons, which was 14,564.67 kilowatts during the monsoon season, while it has generated 2,211.94 kilowatts during the non-monsoon season. And let's take a look at the tidal power generation graph right now. Tawau was recorded to have the highest power generation where it generated 565.61 kilowatts during spring tide and 188.77 kilowatts during neap tide. Now I'm going to talk about a levelized cost of electricity, LCOE. So as we can see here, the LCOE recorded for wave energy is 11.03 cents per kilowatt hour, while tidal energy recorded an LCOE of 36.42 cents per kilowatt hour. What we can take away from here is wave energy achieved a lower LCOE because it requires simpler installations compared to tidal energy, and the tidal energy requires higher capital investment. That is all from me. Thank you very much.
Thank you, Govin. Now I will talk about environmental analysis of wave and tidal energy. In environmental benefit aspects, wave energy can lower greenhouse gases emission because wave energy converters do not release harmful pollutants such as carbon dioxide or nitrogen dioxide. It also can minimize land usage as offshore deployment is on the ocean and lower global warming impact and support aquaculture and hybrid offshore renewable systems. Despite these advantages, wave energy also consists of environmental risks such as underwater noise, which may affect marine organisms relying on echolocation, habitat disturbance caused by cable installation, sediment changes, and chemical leakage from anti-corrosion substances. For tidal energy, the environmental benefits include reducing pollutants such as carbon dioxide and nitrogen dioxide and dust particle emissions. Wave energy is also highly predictable based on reliable lunar cycle, has low ecological risk when proper environmental monitoring is in place, and long operational lifetime with stable power generation. The environmental risks of tidal energy include habitat alteration due to tidal barrage installation, sedimentation changes, potential modification of water levels near tidal barrage, and highly site-dependent where proper mitigation strategies are essential. For our final site selection, we will choose Bintulu as our research wave site location within East Malaysia and Tawau as tidal site location. This is because both of them produce most energy during monsoon and non-monsoon season and spring tide and neap tides. As you can see from this image, after doing research, we have found out that 13.86 km away from Tanjung Kindurong in Bintulu is the best location to install point absorbers with an area of 7.6 km square to produce highest power and connect to the lot. While 4.26 km from Tawau, Kowi Bay Resort is the best location to install tidal energy harvesting technologies with a basin area of 0.648 km square in this image to produce highest tidal energy during both spring tide and neap tide. Next, I will discuss on technologies to enhance durability and reliability of both wave and tidal energy systems. When operating these systems in the ocean, the biggest issue is corrosion. Corrosion is mostly caused by salinity, temperature, alkalinity, and microbial activity, which can weaken structures and cause failure. Sodium chloride concentration significantly affects corrosion rate. There are a few methods that can solve this issue. The first one are polymer coatings. This is the most popular choice because it acts like a big physical shell that keeps seawater from touching the metal. It supports well with standard cathodic protection system, making them a super reliable baseline defense in salty water. Next, we have metal-based coatings. If polymers are just a physical wall, metal coatings add a layer of active defense and wear resistance. They use specific metals or known as sacrificial protection. The coating takes the rust away so the main structure won't affect. These, these are perfect for high salinity area and critical offshore parts that take a serious beating from the environment. Finally, for the absolute worst case condition, we use ceramic-based coatings. It is using tough material like alumina and silica carbide. This method gives an amazing hardness and chemical stability to deal with extreme heat or highly abrasive environments where sand, silt, and wave are constantly grinding against the surface. By matching these three methods, we can make sure these marine structures last longer. In conclusion, Bintulu is our best site location for wave energy, especially during the monsoon, while Tawa is the ideal spot for tidal due to their strong 1.06 meter wave height and 2.75 tidal range respectively. Wave energy is also the more practical choice from economic aspects, with LCOE of 11.03 cents per kilowatt hour compared to tidal LCOE of 36.42 cents per kilowatt hour, which mostly because of installing point absorbers is cheaper than building massive tidal barrage. Ultimately, both give us great low emission power, but to make sure these assets actually survive the harsh ocean environment, investing in anti-corrosion coatings is an ideal solution. And that is all from us. Thank you.